Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists where I make quick turnaround free videos for people during the coronavirus outbreak. If you'd like me to make a video for you, then just contact me, and if I think I can help you, I will. Let me just get this down to the right size. Oh, that's about the right size, good. So hello, hi, hope you're all well. Got an email from Benny in California. A bit distressing to see the wildfires in California. We in Australia have similar sort of problems, so we share that in common, Benny. Now, he's asked me for some help with this. In fact, two problems. I'll talk about this one and then I'll mention the second one. So the first thing I would recommend, Benny, is if you have a look at a video I did recently, just in the last week, something like tips on solving problems, where I go through some of the ideas that you can work through if you're sort of stuck and you don't understand something, you can't progress a problem. So in the spirit of that, what I'm going to do is give you some ideas that I think will help you. And then from then, I think you'll be able to get your mind around it, fill in the sort of cracks that I'm going to leave. Okay, so actually, I haven't even, see, this is where you've got to be careful. So this should actually say be a ring. In fact, why don't we just write it out properly? It's always nice to start a problem right. So I need to be out here. Let R equals the ring of P squared Q be a ring. An algebraic ring where P and Q are prime. The number of ideals in R is, in fact, it was a multiple choice question that Benny showed me, but we'll just explore this. And actually that's the guts of this, is let's explore rather than me just working through the solution. Okay, so the first thing you need to do if you're in this situation is be absolutely clear that you understand what these words are. Ring. Hopefully you know what prime numbers are. It's good to know this, ZP squared Q. What does this mean? So if you've got problems, maybe have a look at an example. I've just, well, let's do Z12. What's that? That's the numbers 0, 1, 2, all up to 11. And remember, with a ring, you need to specify two operations, addition, what we normally call addition and multiplication. In this case, it is addition and multiplication, but it's modulo 12 with addition and multiplication modulo 12. Okay, so in this crazy modulo 12 world, these are the only elements that we have, and when we add and multiply, we do mod 12. So as I go through this, if I see something like 5 times 6, that's 30. But because we're in modulo 12, I'm just going to write, or I might say, or whatever, well, that's 24 plus 6. So I might just write that that's 6. So you need to understand that, and you need to understand what an ideal is. Basically, so I'll go through it in a bit more detail in a sec, but it's a subset of R that has certain properties. Okay, so that was one of the first tips in what I did on the video. Now, the second thing is that don't try and do everything generally. If you can do it, a simplified example or a simple example or a concrete example first. By that I mean is we're just exploring at this point. This is not the answer that you would write in an exam. This is you're just trying to solve the problem at this point. So what I would do is I would go let P equal, say, a low prime like 2, Q equal 3. So the ring is actually Z, what I wrote over here, Z12. So Z12 since 2 squared times 3 equals 12. 2 squared times 3 equals 12. Okay, so at this point, we now start trying to create some ideals. Let's create some, maybe all ideals. Now, you may know a rule for this. If you know the rule, there's a theorem that tells you how to do this. Great. That's not what we're about here. I'm trying to just get you sort of thinking in the right way where you can start to explore these yourself in a better way. Okay. Well, one thing I know is that I'll call it I1, ideal one. The zero set, this is not an empty set, this is the set containing the number 0. Well, that's an ideal. I also know that the ring itself is an ideal, so I can put that one in a sec. I'll talk about why one of them is an ideal in a sec. I'll get to a simplified one. I think this one's an ideal, 2, 4, 6. Well, look, you know, I might start by saying, oh, let's try and create an ideal just with 0, 2. But an ideal has to be closed under addition. In other words, if we add 2 elements of the ideal, we have to stay in the ideal. We have to have the answer must be in the ideal. So when I go 2 plus 2, 2 plus 2 is equal 4. Well, this is not an ideal. This one here is not an ideal because it doesn't have 4. So what I can do is I can actually say, okay, well, okay, that's not an ideal, but maybe this is an ideal. I'll just add 4. But if I add 4 now, 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2, well, I've got to include all of these if it's going to have any chance of being an ideal. 10. Okay, now 10 plus 2 is 12, but 12 is 0 in this modulo world. So we've sort of got to the end of what we can do there. That looks like that may well be an ideal. There's another rule with ideals, and that is that if you take some element of the ideal, so if I take an I in the ideal, I2, and I take any element of the ring, then I has to be in the ring, in the ideal. So the ideal has to be sort of closed under multiplication with the ring. Okay, so here, in this case, this is not a proof, this is just, we're just playing around here, but let's say I take 6 as being the ideal element, and I go 6 by, if I go 6 by 3, 3 is part of the ring, well, that is 18, but 18 is actually, well, 18 is 12 plus 6, so that's actually 6. So I've got 6, and 6 is in the element, is in the ideal I2. So what about 6 times 4? Well, that's 24, which is just 0, which is in the ideal. It's over here. So there's the 0, there's the 6. So you could try, I wouldn't go through them all, but you could try. And you could, I think you could, if you wanted to prove that this is actually an ideal. So let's keep going. What about if we go I'll call this one I3. What about 0, 4? 4 plus 4 is 8. And there we could stop there. That could well be an ideal. I think it is, but I'll leave it up to you to have a play with that. 0, 6 is an ideal. 0, I5, sorry, not 0, 5. I5. Let's do the same thing with 3. 3, 6, 9. That looks like it'd be an ideal. And then the final one is I6, which I'll call 0. Say we start with 1, 2, 3. This is just the ring itself. This is Z12. I think that, well, you probably know that the ring is actually an ideal in itself. Okay, now what would happen if we did, let's try an I7 equals 5. Well, 5 plus 5 is 10. 10 plus 5 is 15. 15 modulo 12 is 3. 10 plus 3, this one here, 10 plus 3 is 13, which is modulo 12 is 1. So 3 plus 1 is 4. 4 plus 1 is 5, we've already done. 5 plus 1 is 6. 6 plus 1 is 7, 8, 9, we've already got 10, we can get to 11, and then 1 plus 1, 1's an element, so 1 plus 1, so 2 is. So if 2 is, in fact, at this point after 2, we've got the whole lot. So this is just I6. So there's no point starting with 0.5 or you're same with 0.7 and that sort of thing. So I'll let you think about all of that. So what it appears to be, let's now have a look back at this, and you might want to prove something about this. But how have we gone about doing this? Well, we've basically said most of them are 0. Well, this one here is 0p, and then it goes on. So we've started it by adding p. This one here is 0p squared, and then we've kept going. This one is 0pq. This one here is 0q. And this one here is 0.1. And then we keep going. And this one, if you like, up here, we could write it as 0, and then we just go straight to p squared q, which is 0 modulo p squared q. So this is really, I've written it this way, but it's really just 0. So when you look above here, if you now direct your eyes up here this way, what's going on here? Well, it seems like every divisor of p squared q creates an ideal. So there's 0. Well, sorry. In the way we've done it up here, this is 12. So I've got 12. P is, this one here is 2. This one is 4. This one, the next one is 6. Then we've got 3. Then we've got 1. So what are these? These are the divisors of 12. And so it appears like and on the video that Benny got me to have a look at, it's the number of divisors of 12 is the answer, or sometimes we give it this symbol. Instead of tau, this one here, you say just dn, or d12, sorry, the number of divisors of 12. Okay, so I think I've said enough there. It depends on how far you, Benny, or anyone else wants to take it in terms of proving things. Now, the next thing that it asked for, the next question was, what about prime ideals? So the number of prime ideals in R. Well, how could you better understand what a prime ideal is, but the starting point would be to, once again, P equals 2, Q equals 3. So we had, well, the first thing that you could say is that every prime ideal has to be an ideal, is an ideal. So we had I1, I2, I3, I4, I5, I6. So we're starting out with 6 of them, but then it's got to be a proper ideal. So every prime ideal is a proper ideal. So this is just from the definition that I'm working on now. If you look up the definition of prime ideal, you'll see it has to be a proper ideal. So what's a proper ideal? Well, a proper ideal can't be the 0 ring ideal, and it can't be the ring itself. So if we go back here, you can see here we've included this one and this one. So we better get rid of them because they're not prime ideals. We know that straight away. So I1 and I6 can go. So we're left with I2, I3, I4, I5. Okay, and now you've got to get into it must be prime. It's a prime ideal. So what does prime mean? Prime ideal. What does it mean apart from what I've written? I mean, the other thing is that it has to be a non-empty subset, but these are all non-empty subsets. But a prime ideal means that if A times B is an is an element of, say, this I don't know, I4 or whatever, whichever of these you're checking, then that must imply that A is an element of I4, B is an element of I4. So let's just run that, go back and have a look. I'll just do one and have a look at one of them. What about I3? In fact, I3, 0, 4, 8. So I3, that was 0, 4, 8. So what does that say? Well, if we take an element, say 4, so AB is an element, equals 8. So we'll let that, sorry, equals 4. Does that imply that A equals, this should say or, by the way, or. A equals, sorry, does that mean that A is an element of I3 or B is an element of I3? Is this true? And the answer is no, it's not true. Not true. Why? 2 times 2 equals 4, but 2 is not an element of I3. So this one is not a prime ideal. Okay, so I think I've left you, Benny, with some ideas of how you could yourself go through this and make some more sense of it. So I'll leave it there. If you've got more questions, by all means, come back and ask. And more generally, if anyone watching this has got any problems in mathematics where they think I might be able to help, then just email me or comment below any of my videos.